Imagine standing on the dusty red plains of Mars, gazing up at a sky that isn't blue but a pale pink, when suddenly your instruments spike. Something invisible is swirling in the thin air around you. Methane, a gas that shouldn't be there, at least not in the quantities we've detected. And that's where the mystery begins, because on Earth, methane usually means life. Cows, swamps, even the tiniest microbes, they all produce it. So when our rovers and orbiters sniffed it out on Mars, the question hit like a lightning bolt. Is this the first whiff of alien life? Or could it be something even wilder? For years, scientists have been chasing this enigma like detectives, piecing together a cosmic puzzle. The numbers don't add up. Mars's methane comes and goes in unpredictable bursts, vanishing as quickly as it appears. Some say it's proof of underground microbes, tiny Martians, quietly farting their way through the millennia. But others, they've dared to suggest something far more extraordinary. What if the methane isn't just biological? What if it's a sign of something engineered? An underground civilization hidden beneath the rust-colored soil, venting gases as they go about their unfathomable business. Sounds like science fiction, right? Yet here's the twist. Both theories are backed by serious science, and both could change everything we think we know about life in the universe. This isn't just about gas on a distant planet. It's about the tantalizing possibility that we're not alone, that somewhere beneath the barren surface of Mars, there might be creatures tiny, or perhaps not so tiny, going about their lives completely unaware of us, staring up at their world. Or maybe, just maybe, they're staring back. Today, we're diving deep into the evidence, the controversies, and the mind-bending implications of Mars's methane mystery. By the end, you might find yourself questioning not just what's possible on Mars, but what's possible everywhere. So buckle up, because whether it's microbial farts or alien exhaust, one thing's for sure: the truth is out there, and it's stranger than we ever imagined. The discovery of methane on Mars wasn't just surprising, it was downright baffling. Here's why. On Earth, methane is everywhere, from the burps of livestock to the bubbling depths of wetlands. But almost all of it traces back to living things. Microbes, plants, even termites, they churn it out as part of their natural processes. So when the European Space Agency's Mars Express orbiter first detected traces of methane in the Martian atmosphere back in 2004, scientists sat up straight. Because if life makes methane, and Mars has methane, well, you see where this is going. But here's the catch: Mars shouldn't have methane, at least not floating around like this. The planet's thin atmosphere is bathed in ultraviolet radiation from the sun, which breaks methane molecules apart in just a few hundred years. That means any methane we detect today had to have been released very recently. And yet, it keeps appearing in sporadic, unpredictable bursts, sometimes vanishing within weeks. It's like someone's turning a faucet on and off underground. That's where things get really interesting. Scientists have come up with two leading explanations, and both are as fascinating as they are controversial. The first, tiny Martian microbes, tucked away beneath the surface, might be producing methane just like earthly bacteria do. These hypothetical organisms could be clinging to life in underground aquifers or geothermal vents, turning simple chemical reactions into gas. It's not impossible after all. Life thrives in the most extreme places on Earth, from boiling hot springs to Antarctic ice. But there's another, even more tantalizing possibility. Mars is geologically active in ways we're only beginning to understand. Volcanic activity deep underground could be heating rocks rich in minerals like olivine, triggering chemical reactions that release methane naturally. No life required. The problem: we've yet to find definitive proof of active volcanoes or recent lava flows on Mars, so while geology can't be ruled out, the lack of smoking guns literally keeps the mystery wide open. What makes this debate so thrilling is how high the stakes are. If the methane is biological, it rewrites the story of life in the universe. If it's geological, it reveals a Mars far more dynamic than we ever imagined. Either way, something strange is happening beneath that rusty surface, and every new clue brings us closer to an answer that could change everything. The idea of Martian microbes quietly producing methane beneath the surface isn't just science fiction. It's a serious scientific hypothesis with roots right here on Earth. Meet methanogens, the microscopic powerhouses that could hold the key to this mystery. These tiny organisms thrive in places where most life would perish, deep in ocean trenches, buried in permafrost, even inside the guts of termites. They don't need oxygen. They don't even need sunlight. All they require are simple ingredients like carbon dioxide and hydrogen, which they metabolize into methane as a byproduct. If life exists on Mars, methanogens are among the top contenders for how it might survive. But how could these microbes endure on a planet so harsh? Mars's underground might be their perfect refuge. Imagine layers of ice and rock shielding them from the deadly radiation above, with pockets of liquid water kept just warm enough by geothermal heat or chemical reactions. We've already found extremophiles on Earth in equally brutal environments, bacteria flourishing in acidic mine drainage, or colonies thriving near hydrothermal vents under crushing ocean pressures. If life can cling to existence in those places, why not beneath the Martian soil? The parallels are striking. In Antarctica's dry valleys, one of the most Mars-like places on Earth, microbes survive in frozen, hyper-arid conditions by extracting water from minerals. On Mars, similar processes could be at work. Salty subsurface brines might stay liquid at colder temperatures, creating tiny oases for microbial communities. Even more compelling, some methanogens on Earth can enter a dormant state for centuries, waiting out extreme conditions until their environment becomes habitable again. If Martian microbes exist, they could be doing the same, waking up periodically when conditions briefly improve, releasing methane in fleeting bursts that match the erratic patterns we've observed. Yet for all the tantalizing possibilities, challenges remain. Mars's subsurface is likely far drier and colder than even the harshest earthly environments. Without a steady energy source, like the geothermal vents that feed deep-sea ecosystems, any microbes would need another way to sustain themselves. Some scientists speculate they might rely on chemical reactions between water and minerals like olivine, a process called serpentinization, which produces hydrogen, a potential food source. Others suggest radioactive elements in Martian rocks could provide just enough warmth and energy to keep microbial communities ticking over. What makes this theory so electrifying isn't just the science, it's the implications. If methanogens are indeed responsible for Mars's methane, it would mean life isn't a fluke confined to Earth. It would suggest that life can spark wherever there's even a sliver of opportunity, adapting to the most hostile corners of the universe. And if that's true on Mars, why not on the icy moons of Jupiter and Saturn, or the countless exoplanets scattered across the galaxy? The discovery of a single microbe beneath the Martian surface wouldn't just solve a mystery, it would rewrite the story of life itself. Of course, not everyone's convinced. critics point out that non-biological processes could mimic these methane signatures, and until we drill deep into Mars's crust or catch a microbe in the act, the debate will rage on. But that's the beauty of science. It thrives on unanswered questions. Whether Mars's methane comes from living farts or ancient geology, one thing's certain: the red planet still has secrets to spill, and we're only just beginning to listen. If we want to understand how life might survive on Mars, we don't need to look further than our own planet. Earth is teeming with extremophiles, organisms that flourish in conditions once thought utterly inhospitable. These microbial survivalists laugh in the face of extremes, thriving in boiling water, crushing pressures, and even radiation levels that would kill most living things. And if life can cling to existence in these nightmarish environments on Earth, why not beneath the Martian surface? Take the deep sea hydrothermal vents, for example. These underwater geysers spew superheated, mineral-rich water into the icy darkness of the ocean floor. Temperatures can soar past 400 degrees Fahrenheit, and the pressure is enough to crush a submarine. Yet entire ecosystems thrive here, fueled not by sunlight, but by chemosynthesis, a process where microbes convert chemicals like hydrogen sulfide into energy. The parallels to Mars are uncanny. If hydrothermal vents exist beneath the Martian crust, could similar microbes be eking out an existence there, too? Then there's Dalal, a volcanic crater in Ethiopia's Danakil Depression. Its acidic, salt-saturated pools glow neon yellow and green, with pH levels so low they can dissolve metal. It's about as close to hell on Earth as you can get, and yet life persists. Tiny archaea microbes so tough they're often called extremophiles of extremophiles have been found thriving in these toxic waters. What's fascinating is how similar these conditions are to certain regions on Mars, where acidic salts and evaporative minerals hint at a past, or even present briny habitat. If microbes can survive Dalal's deadly chemistry, could they also withstand the harshness of Martian soil? Even more mind-bending are the microbes found buried deep in permafrost or trapped inside crystals of salt for millions of years. In Siberia's frozen tundra, scientists have revived bacteria that had been dormant for tens of thousands of years simply by warming them up. On Mars, where permafrost blankets much of the subsurface, similar microbes could be lying in wait, occasionally waking up when geothermal heat or seasonal changes create fleeting pockets of liquid water. Perhaps the most striking analogy comes from underground caves like Mexico's Cueva de los Cristales, where crystals the size of telephone poles grow in blistering heat and near total darkness. Here, microbes survive by feeding on iron and sulfur compounds, elements we know exist in abundance on Mars. If life can find a way in these lightless, mineral-heavy labyrinths, why not in the labyrinthine fractures beneath Mars's surface? What these earthly extremophiles teach us is that life is far more adaptable than we ever imagined. It doesn't need paradise, just a sliver of opportunity. And if Mars has even a fraction of the hidden oases that Earth does, the odds of finding life there suddenly don't seem so far-fetched. The question isn't just whether Mars could host life. It's whether we've been underestimating life's sheer tenacity all along. Beneath the barren, rust-colored surface of Mars, there may be an entire hidden world of liquid water, vast reservoirs that could rewrite our understanding of life's potential in the cosmos. While the planet's surface is frozen and desolate today, evidence suggests that deep below, pockets of water might still persist, trapped in briny aquifers or even sprawling subsurface lakes. These aren't just puddles, Some scientists believe Mars could harbor entire oceans worth of water beneath its crust, buried but not gone. And where there's liquid water, there's always the tantalizing possibility of life. The clues start at the poles. Mars' ice caps, gleaming under the weak sunlight, aren't just made of frozen carbon dioxide. They contain massive deposits of water ice, layered like a cosmic wedding cake. But it's what lies beneath that's truly intriguing. In 2018, the European Space Agency's Mars Express orbiter made a bombshell discovery using radar: a 20-kilometer-wide lake of liquid water buried under the southern ice cap, nearly a mile beneath the surface. Even more astonishing, the water wasn't frozen solid, despite temperatures far below zero. How? The answer lies in salt. Dissolved minerals could act like antifreeze, lowering the freezing point and keeping the water liquid, even in Mars' deep chill. This wasn't a one-off find. Subsequent studies hinted at a network of similar buried lakes, suggesting that Mars' subsurface might be far wetter and far more dynamic than we ever imagined. Some researchers speculate these briny pockets could be connected, forming a sprawling underground web of aquifers, slowly shifting and flowing over millennia. It's a haunting echo of Earth's own subterranean water systems, like the hidden rivers beneath Antarctica or the vast, dark oceans inside moons like Europa. But here's the real kicker. On Earth, wherever we find liquid water, we find life. From the sunless depths of underground caves to the crushing pressures of hydrothermal vents, life finds a way to persist. If Mars has these hidden oases, why couldn't they too host microbes? Picture extremophiles, those tenacious earthly survivors adapted to Mars' salty, lightless depths, thriving in slow-motion ecosystems fueled by chemical reactions rather than sunlight. They wouldn't need much, just a trickle of geothermal warmth, a dash of dissolved minerals, and lots of time, to eke out an existence. The implications are staggering. If life took root in Mars' ancient oceans billions of years ago, as many scientists believe, it might not have vanished when the surface dried up. It could have retreated underground, clinging to these buried wet refuges like cosmic survivors waiting out an eternal winter. Every new discovery, every radar ping that reveals another hidden lake brings us closer to answering the ultimate question: are we alone, or is Mars, silent and still on the outside, quietly teeming beneath the surface? Of course, not everyone's convinced. Some argue these lakes could be illusions, layers of clay or slushy ice mimicking liquid water in radar data. Others point out that without a clear energy source, like hydrothermal activity, any microbes would struggle to survive. But then again, we've been wrong before. Life has a habit of showing up where we least expect it, in conditions we once thought impossible. Until we drill through that ice, until we taste that briny water for ourselves, the mystery remains. And that's what makes this search so thrilling, because hidden beneath the dust and rock of Mars, there might be answers or even neighbors we've only just begun to imagine. What if Mars's methane has nothing to do with life at all? Before we get carried away picturing underground microbes or secret alien cities, there's another possibility, one that doesn't require a single living organism. The gas could be coming from the planet itself, produced by ancient geological processes that have nothing to do with biology. This might sound disappointing at first, but the science behind it is just as fascinating, and in some ways, even more surprising. Let's start with serpentinization, a mouthful of a word that describes one of the most methane-friendly reactions in the universe. Picture this: deep underground, water seeps through cracks in Mars's crust, coming into contact with minerals like olivine, a greenish, iron-rich rock that's common in both Earth's mantle and Martian meteorites. When water meets these minerals under the right conditions, a chemical ballet begins. The water molecules split, their oxygen atoms bonding with the rock, while the leftover hydrogen reacts with carbon dioxide or carbon monoxide in the surrounding environment. The result, methane, bubbling up from the depths without a single microbe lifting a finger. Here's the kicker: we've seen this happen on Earth. In places like the Lost City hydrothermal field in the Atlantic Ocean, serpentinization churns out methane constantly, fueling entire ecosystems of weird, otherworldly life. But the process itself doesn't need life. It's pure chemistry, a planetary exhale that could be happening right now beneath Mars's barren surface. And given that olivine has been detected all over the red planet, from its vast volcanic plains to the dust in its atmosphere, the ingredients for serpentinization are definitely there. But geology has more tricks up its sleeve. Volcanic activity, though seemingly dormant on Mars today, might not be completely extinct. On Earth, active volcanoes release traces of methane alongside other gases like sulfur dioxide and carbon dioxide. If Mars has even residual magma pockets deep underground, or if its last eruptions were more recent than we think, those ancient lava flows could still be venting methane through cracks and fissures. The problem, we haven't found smoking guns literally. No active volcanoes, no fresh lava plains, no plumes of volcanic gas. Still, absence of evidence isn't evidence of absence. Mars is big, and we've barely scratched its surface. Then there's meteorite magic. When space rocks rich in carbon slam into Mars, the intense heat and pressure of impact can forge methane in seconds. It's like striking a cosmic match, one that doesn't need life, volcanoes, or even underground water to spark. And given how often Mars gets pummeled by asteroids and comets, this could account for at least some of the methane spikes we've detected. The beauty of these abiotic explanations is how elegantly they sidestep the need for biology. They show us that a planet can breathe, chemically speaking, without being alive. But here's the twist: even if Mars's methane turns out to be geological, that doesn't make it mundane. These processes paint a picture of a world that's far more dynamic than its dead, dusty surface suggests, one with hidden water, simmering chemistry, and maybe even the occasional underground rumble. And who knows, if serpentinization is happening on Mars today, it might be creating something just as precious as life, environments where life could one day take root. After all, before biology, there was chemistry, and Mars, it seems, still has plenty of that. Mars may look like a frozen wasteland today, but scratch beneath the surface literally, and you'll find clues to a fiery past. Towering volcanoes, some 3 times the height of Mount Everest, dominate the landscape, their slopes carved by ancient lava flows that once raged across the planet. Olympus Mons, the solar system's largest volcano, is so massive its peak pierces the thin Martian atmosphere. These aren't just relics, they're proof that Mars was once a world of fire and fury. But here's the million-dollar question: is that volcanic energy truly extinct, or could there still be embers smoldering beneath the dust? Recent discoveries suggest Mars might not be as geologically dead as we thought. In 2021, scientists analyzing satellite images spotted something startling. A region called Elysium Planitia showed signs of what looked like fresh lava flows, perhaps as recent as 200,000 years ago. That's a blink of an eye in planetary time. Even more intriguing, seismic data from NASA. InSight lander detected marsquaks rumbling through the planet's crust, hinting at molten rock shifting deep below. If magma is still moving, even sluggishly, It could mean Mars's volcanoes are merely sleeping, not dead. Now, tie that back to methane. Volcanic activity doesn't just spew lava, it releases gases, including methane. On Earth, active volcanoes like those in Hawaii or Iceland constantly vent trace amounts of the gas. If Mars has even pockets of residual magma, heated chambers where old volcanic plumbing still simmers, they could be leaking methane through cracks in the crust. No microbes needed. The gas might build up underground until pressure forces it out in sporadic bursts, matching the unpredictable spikes we've observed. But here's where it gets really wild. Some researchers propose that Mars's volcanic heat could be doing double duty, not just producing methane directly, but also creating the perfect conditions for serpentinization. Imagine underground hotspots where magma warms icy rock, melting just enough water to trigger those methane-producing chemical reactions. It's a one-two punch of geology, heat fueling chemistry, chemistry fueling mystery. Of course, skeptics argue that without definitive proof, like an active eruption caught on camera, volcanic methane remains speculative, yet absence of evidence isn't evidence of absence. Mars is vast, and our rovers have barely explored a fraction of its surface. Hidden beneath the regolith, there could be networks of magma channels, slowly cooling but still hot enough to whisper secrets through tremors and gas. Whether Mars's volcanoes are extinct, dormant, or just playing hard to get, their legacy is undeniable. They shaped the planet's past, and they might still be shaping its present. And if even a flicker of that ancient fire persists, it could rewrite what we know about Mars not as a dead world, but as a planet with a pulse, quietly ticking beneath the rust. One of the strangest things about Mars methane isn't just that it's there, it's that it refuses to stick around. Imagine lighting a candle in a windy room, only for the flame to vanish the moment you blink. That's what scientists are dealing with here. Methane keeps appearing in sudden, localized bursts, sometimes spiking to concentrations 10 times background levels, only to dissipate within weeks. This isn't how methane behaves on Earth, where it lingers for years. So what's stealing Mars methane so quickly? The answer might rewrite what we know about the planet's hidden chemistry. The first suspect is sunlight. Mars' thin atmosphere offers little protection from ultraviolet radiation, which tears methane molecules apart through a process called photodissociation. On Earth, our thick ozone layer shields methane from this fate, giving it a lifespan of around a decade. But on Mars, exposed to the sun's unfiltered fury, methane should still last about 300 years, far longer than the weeks or months we're observing. Clearly, something else is speeding up the destruction. Enter the mystery of oxidizing agents. Mars' soil is packed with perchlorates, corrosive salts that react violently with organic compounds. When methane drifts close to the surface, these salts could be acting like cosmic sponges, soaking it up and breaking it down in chemical reactions. It's a process we've seen in labs. Perchlorates exposed to simulated Martian conditions devour methane at rates that match the strange disappearance. But here's the twist: perchlorates shouldn't work this fast either. Even with their help, calculations suggest methane ought to linger longer than it does. That's led scientists to an even wilder theory: electrostatic dust storms. Mars is infamous for its planet-wide dust devils, which generate static electricity as particles collide. Some researchers propose these charged dust grains could be acting like microscopic reactors, catalyzing reactions that obliterate methane in record time. Picture trillions of tiny lightning bolts, each one zapping methane out of existence. It's a radical idea, but lab experiments show electrified sand can indeed destroy methane faster than sunlight or salts alone. Yet none of these explanations fully account for the methane's patchy, unpredictable behavior. If destruction were uniform, the gas should fade evenly across the planet. Instead, it vanishes from some areas while lingering stubbornly in others, almost as if something underground is replenishing it in select spots. This has led to whispers of seasonal underground storage, where methane might get trapped in icy cages called clathrates during colder months, only to be released when temperatures rise. Whatever the culprit, this ephemeral nature makes methane maddeningly hard to study. Every time we think we've caught it in the act, it slips away, leaving us with more questions than answers. But that's what makes this mystery so thrilling, because if we can crack the case of Mars' disappearing methane, we might not just solve a planetary puzzle. We could uncover entirely new chemistry hidden in the red planet's dust and shadows. When the Curiosity rover touched down in Gale Crater in 2012, it brought with it the most sophisticated chemical lab ever sent to another planet. Among its many tools was a laser spectrometer designed to sniff out methane with precision down to parts per billion. What it found would send shockwaves through the scientific community. Over months and years of careful measurements, Curiosity detected something baffling: methane levels that didn't just fluctuate, but did so in dramatic, unpredictable spikes. One week, the air might show barely a trace. The next, concentrations could surge tenfold before vanishing again as quickly as they appeared. One of the most startling moments came in late 2013, when Curiosity recorded a methane spike lasting just 60 Martian days, levels soaring to nearly 7 parts per billion before collapsing back to baseline. Then, in 2019, an even bigger surprise, a reading of 21 parts per billion, the highest concentration ever detected on Mars. These weren't subtle variations. They were bursts like someone turning a gas tap on and off deep underground. But here's what makes these findings even more intriguing. The methane didn't behave like a global atmospheric phenomenon. It was hyperlocal, often confined to Gale Crater or its immediate surroundings. That suggests the gas wasn't drifting in from distant sources, but being released nearby, perhaps through cracks in the ground or porous rock formations. When scientists mapped the timing of these spikes, another pattern emerged. Many coincided with warmer seasons on Mars, when temperatures might be just high enough to melt thin layers of subsurface ice, releasing trapped methane like bubbles fizzing from a soda can. Yet for all these tantalizing clues, Curiosity's data also deepened the mystery. The rover's instruments detected no methane at all during some periods, only for it to reappear months later. Even more puzzling, orbital observations from the European Space Agency's Trace Gas Orbiter often failed to confirm Curiosity's ground-level detections. Some scientists argue this discrepancy points to rapid methane destruction in the atmosphere, something obliterating the gas before satellites can spot it. Others wonder if the rover itself might be stirring up ancient methane trapped in surface soils, creating fleeting pockets of detectable gas. What's clear is that these findings rule out simple explanations. If the methane were purely geological, say, from ongoing volcanic activity, we'd expect steadier, more widespread emissions. Biological sources, on the other hand, could explain the irregular bursts, as microbial communities might release gas in fits and starts depending on environmental conditions. But without drilling deeper or capturing a definitive organic signature, the question remains open. Curiosity's greatest legacy here might be proving that Mars methane isn't just a scientific curiosity, It's a dynamic, evolving puzzle. Every spike, every disappearance, every conflicting dataset adds another piece to the mystery. And as long as the rover keeps sniffing the Martian air, we'll keep inching closer to an answer that could change how we see our place in the cosmos. The ExoMars Trace Gas Orbiter should have been the definitive answer to Mars' methane mystery. Launched in 2016 as a collaboration between the European Space Agency and Russia's Roscosmos, this high-tech satellite was designed to map atmospheric gases with unprecedented precision, capable of detecting methane at concentrations as low as 50 parts per trillion. Yet when it started scanning the planet from orbit, something bizarre happened. While a Curiosity rover was catching whiffs of methane down in Gale Crater, the Trace Gas Orbiter found almost nothing. Not just lower readings near zero methane across entire hemispheres of Mars. This contradiction isn't just a scientific hiccup, it's a full-blown enigma that's forced researchers to rethink everything from instrument sensitivity to the very nature of Martian methane itself. One theory hinges on timing. The orbiter's instruments take measurements in the early afternoon, when sunlight heats the surface and stirs up atmospheric turbulence. Curiosity, meanwhile, does its sniffing at night, when the air near the ground grows still. If methane is seeping from underground only to be rapidly destroyed by daytime chemistry, like those electrostatic dust reactions, the orbiter might literally be missing the gas by hours. Then there's altitude. The Trace Gas Orbiter scans the atmosphere several kilometers up, while Curiosity samples air at ground level. If methane isn't mixing uniformly, if it's staying trapped near the surface, the rover would catch plumes the satellite never sees. Some models suggest Mars methane might behave like fog hugging a valley floor, dense in certain spots but invisible just a few meters higher, but the plot thickens. In 2021, the orbiter finally detected traces of methane not in the air, but in a peculiar way. As sunlight passed through the atmosphere, very faint absorption lines appeared at wavelengths matching methane. The kicker: these signals were strongest over Curiosity's location in Gale Crater. It's as if the satellite finally caught a fleeting glimpse of what the rover's been smelling all along. What makes this discrepancy so fascinating is what it implies about Mars itself, a gas that appears and vanishes not just over time, but across vertical slices of atmosphere, suggests an environment far more chemically active than we ever imagined. It's possible we're seeing the aftermath of some unknown process, methane being produced, destroyed, or transformed in ways we haven't yet identified. The real lesson here might be humility. Two of humanity's most advanced instruments, one on the ground and one in orbit, are giving us wildly different portraits of the same planet. And that's the beauty of science. Sometimes the most revealing discoveries aren't answers, but better questions. Until we land a fleet of sensors across Mars or drill deep into its crust, this methane mystery will keep us guessing, proving once again that the red planet guards its secrets well. Now let's venture into territory where science blurs with speculation, where methane isn't just a gas, but a cosmic breadcrumb leading to something far more extraordinary. What if the source isn't geology or microbes, but an underground civilization? It sounds like the plot of a pulp sci-fi novel, but this idea has roots in both fiction and serious, if fringe scientific debate. From H.G. Wells' War of the Worlds to modern conspiracy theories, the notion of Martians lurking beneath the surface has fascinated humanity for over a century. But could there be a sliver of plausibility hidden beneath the fantasy? The theory goes like this: Mars' surface became uninhabitable eons ago, its atmosphere stripped away by solar winds. But deep underground, shielded from radiation and cold, a technologically advanced society might have retreated, surviving in vast caverns or even constructing sprawling artificial habitats. Their machinery, industry, or even waste systems could theoretically produce methane as a byproduct, venting it to the surface through natural fissures or old volcanic conduits. It's an intoxicating idea, one that turns the red planet's barren face into a mask hiding unimaginable secrets. The seeds of this hypothesis didn't sprout from nowhere. In the late 19th century, astronomers like Percival Lowell mapped what he believed were canals on Mars' artificial waterways built by a dying civilization. Though we now know these were optical illusions, they fueled decades of speculation. Fast forward to the 21st century, and satellite images of skylights, strange, shadowed pits that could be cave entrances, reignited the conversation. Some researchers argue these formations might lead to subterranean networks large enough to shelter entire ecosystems or societies. But here's where we hit the reality check. For all its allure, the civilization theory faces a mountain of scientific skepticism. First, there's the energy problem. Sustaining an advanced society requires staggering amounts of power, think geothermal taps or nuclear reactors, yet we found zero evidence of such infrastructure, no heat signatures or radioactive traces. Second, methane alone is flimsy evidence. Even if it were being artificially produced, without corroborating signs like industrial chemicals or structured radio signals, it's indistinguishable from natural processes. Yet the theory persists, partly because science hasn't outright killed it. We've barely scratched Mars' subsurface, and nature constantly surprises us. Take Earth's own extreme habitats, entire cities of tube worms thriving around hydrothermal vents, or bacteria living in rocks miles underground. If life can flourish in those hidden realms, why not intelligence under Mars? It's a stretch, but not an impossible one, just one that demands extraordinary proof. Perhaps the most compelling argument against the civilization angle isn't scientific, but philosophical. If a society advanced enough to build underground metropolises existed, wouldn't they have left more conspicuous footprints, satellites, surface structures, or even attempts to communicate? Unless, of course, they're intentionally hiding, and that's where the line between hypothesis and folklore truly blurs. Whether you dismiss this as fantasy or entertain it as a remote possibility, the underlying truth remains. Mars' methane mystery exposes how little we truly know. Every time we think we've pinned it down, to microbes, to rocks, to hidden lakes, it slips away, leaving room for wonder. And in that gap between knowledge and imagination, even the wildest ideas get to breathe, if only for a moment. After all, the universe has surprised us before. Why not again? If an advanced civilization were thriving beneath Mars' surface, how exactly might they be producing the methane we've detected? The answer could lie in something we know all too well here on Earth: industrial activity. Human society generates methane in countless ways, from landfills decomposing organic waste to livestock digestion and even leaky natural gas pipelines. An alien civilization, especially one confined to underground habitats, might rely on similar processes just scaled to Martian conditions. Picture vast subterranean farms cultivating microbial or fungal-based food sources, exhaling methane as a byproduct. Or imagine waste treatment systems breaking down organic matter in oxygen-starved environments, releasing pockets of gas that eventually seep to the surface. On Earth, anaerobic digesters do exactly this, turning sewage and agricultural waste into usable energy, and plenty of methane. But industry doesn't stop at waste. Advanced technology could be tapping into Mars' natural resources, processing minerals or extracting water through chemical reactions that unintentionally produce methane. Take hydrogen extraction, for example. If a civilization were splitting water ice into hydrogen and oxygen for fuel or life support, side reactions with carbon-rich minerals might generate methane as an industrial byproduct. We've seen analogous processes in Earth's energy sector, where fracking and cold methane extraction release the gas during resource harvesting. The difference: on Mars, there'd be no regulations or containment systems to prevent leaks. Then there's the possibility of energy production itself. On Earth, burning fossil fuels releases methane indirectly through incomplete combustion. An underground Martian society might rely on fusion reactors, geothermal taps, or even nuclear power, all of which could involve coolant systems or chemical cycles that vent trace gases. Even something as futuristic as methane-based rocket propellant production, if scaled up, might leave atmospheric fingerprints. After all, SpaceX's Starship uses methane as fuel, and manufacturing it on Mars would require massive infrastructure. If aliens were doing the same, could their refineries be the source of these mysterious plumes? Yet the most intriguing parallel might come from an unexpected place: climate engineering. On Earth, scientists have debated pumping methane into the atmosphere to warm polar regions, a controversial geoengineering concept. If Mars' underground dwellers were trying to terraform their planet's surface over millennia, controlled methane releases could be part of a long-term plan to thicken the atmosphere and trap heat. It's a stretch, but so is every theory about alien civilizations. The point isn't whether these scenarios are likely, it's that they're possible. And in the search for answers, even the wildest ideas deserve a moment under the microscope. The beauty of this thought experiment is how it forces us to question our assumptions. Methane is methane, whether it's made by microbes, rocks, or reactors. Without more data, we're left reading cosmic tea leaves, interpreting faint chemical signals that could mean anything. But that's the thrill of science, at the edge of the unknown. Every whiff of methane, every fleeting spike, is a whisper from a world that refuses to reveal its secrets easily. And whether the source is mundane or miraculous, the pursuit of that truth is what keeps us looking up and digging deeper. Beneath the cracked and cratered surface of Mars, there may lie a hidden labyrinth of colossal tunnels, ancient highways, carved not by water, but by fire. These are lava tubes, the skeletal remains of rivers of molten rock that once flowed beneath Mars' volcanic plains. On Earth, such formations are modest, rarely wider than a subway tunnel. But on Mars, satellite images and ground-penetrating radar reveal tubes stretching hundreds of meters across, large enough to swallow entire city blocks. These aren't just geological curiosities. They could be the perfect refuges for life, natural bunkers shielding delicate organisms, or even complex beings from the deadly radiation that bombards Mars' surface. Picture walking into one of these caverns. The ceiling arches high overhead, its walls smooth from the lava that once poured through like liquid fire. Sunlight filters in through collapsed sections, casting eerie beams onto a floor littered with rubble. The temperature here is stable, hovering around -50 degrees Celsius, frigid by Earth standards, but far gentler than the surface's wild swings between boiling and freezing. Most crucially, the rock overhead acts like a cosmic umbrella, blocking up to 82% of the solar and cosmic radiation that sterilizes the outside world. On a planet where surface radiation levels would give an astronaut a lethal dose in months, these tubes could be oases of relative safety. Astrobiologists are particularly fascinated by what might lurk in these shadowed halls. On Earth, life thrives in similar environments. Bacteria cling to the walls of lava tubes in Iceland and Hawaii, surviving on minerals and the faint trickle of water seeping through cracks. Some tubes even harbor entire ecosystems, like the caves of New Mexico, where microbes derive energy not from sunlight, but from iron and sulfur compounds in the rock. If Earth's lava tubes can host such tenacious life, why not Mars? The red planet's tubes are older, drier, and colder, but they share one critical feature: stability. In a subsurface void protected from radiation and temperature swings, organisms could persist for millennia, metabolizing slowly in the darkness. But microbes aren't the only hypothetical inhabitants. Those massive tube dimensions have led some researchers, and more than a few science fiction writers, to speculate about larger occupants. Could an intelligent species have retreated underground as Mars' surface grew inhospitable, turning these tunnels into a sprawling subterranean habitat? It's a stretch, but not entirely implausible. The largest Martian lava tubes could easily accommodate structures, transportation networks, or even agriculture under artificial light. Without the need to build radiation shielding from scratch, a civilization might repurpose these ready-made arcologies, venting waste gases like methane through surface fractures. Of course, the biggest hurdle is evidence, or rather, the lack of it. While orbital images show clear pit entrances to potential lava tubes, no mission has yet ventured inside. Upcoming projects, like NAS, a proposed Moon-to-Mars planetary autonomous lava tube explorer, aim to send robots into these voids, mapping their contours and sniffing for chemical traces of life. Until then, the tubes remain tantalizing blanks on Mars' map, dark, silent, and full of possibility. Whether they shelter microbes, intelligent beings, or nothing but ancient dust, these lava tubes are more than geological relics. They're time capsules, preserving what may be the last habitable niches on a world that dried up billions of years ago. And if life, or its remnants, still clings to existence on Mars, this underground maze might be where we finally find it. The door is open, we just have to step inside. Billions of years ago, Mars wasn't the frozen desert we see today. It was a world teeming with possibility. Rivers carved valleys wider than the Grand Canyon. Storms raged over oceans deeper than the Mediterranean. And volcanoes pumped enough carbon dioxide into the air to trap warmth against a younger, fainter sun. This was a Mars with liquid water pooling on its surface for millions of years. A Mars that might have whispered to life the same way Earth did. But could that life have climbed beyond microbes? Could an intelligent species have risen beneath those alien skies, only to vanish when the planet's heartbeat slowed? The evidence for Mars' watery past is etched across its surface like a ghostly blueprint. Orbiters have mapped the remains of ancient shorelines, jagged cliffs that once overlooked vast northern oceans, now dry as bone. The Curiosity Rover rolled across what scientists believe was the bed of an ancient lake in Gale Crater, its wheels churning up sediments rich in clay minerals that only form in the presence of water. Even more telling are the networks of river valleys that spiderweb the planet, some stretching thousands of kilometers, their branching patterns identical to watersheds on Earth. These aren't the work of fleeting floods, but persistent flows that lasted centuries or longer. Put simply, Mars didn't just have water, it had weather, seasons, and a hydrological cycle that mirrored our own. But here's the spine-tingling part. For life to evolve beyond single-celled simplicity, it needs stability, a consistent environment where complexity can emerge over generations. Earth took nearly 2 billion years to go from microbes to multicellular life. Mars' window of habitability, by contrast, might have snapped shut after just a few 100 million years. As the planet's core cooled, its magnetic field weakened, allowing solar winds to strip away the atmosphere. Oceans evaporated, rivers froze, and the surface became the irradiated wasteland we know today. That timeline seems impossibly tight for intelligence to arise unless life got a head start. Some astrobiologists speculate that Mars could have been a cradle for life even before Earth was habitable. While our planet was still a molten hellscape, bombarded by asteroids during the late heavy bombardment, Mars, smaller and quicker to cool, might have offered a tranquil oasis. If life emerged there first, it could have gained a crucial evolutionary jump-start. We know microbes on Earth can survive asteroid impacts, hitching rides on ejected debris. Could Martian life have seeded Earth via meteorite, making us the descendants of a civilization that perished next door? It's a wild idea, but not impossible. After all, we found Martian meteorites on Earth bearing tiny structures that resemble fossilized bacteria. The real clincher, though, lies beneath the surface. If an advanced species did arise on Mars, they'd have faced a dying planet much earlier than we will on Earth. Their response might mirror what we're contemplating today: underground migration. Imagine vast cities carved into bedrock, powered by geothermal energy, their inhabitants retreating deeper as the surface grew lethal. We've already spotted what look like artificial structures in satellite images, oddly symmetrical mounds in Arabia Terra, or the infamous face on Mars that turned out to be a trick of light. Most have mundane explanations, but a handful remain stubbornly enigmatic. The tragic irony: just as we're developing the tools to uncover these secrets, Mars is erasing them. Dust storms sandblast the surface, burying artifacts under meters of rust-colored powder. Cosmic radiation fries organic molecules left in the open. If an ancient Martian civilization existed, its remnants might be fading to dust just as we're learning where to look. That ticking clock makes every rover, every orbital scan, every soil sample feel urgent, because the red planet isn't just a mystery. It might be a graveyard, its secrets crumbling under the weight of time. The idea that life might have hitchhiked between planets on meteorites sounds like something straight out of a sci-fi movie, but it's a real scientific theory with a name: panspermia. Picture this: a massive asteroid slams into Mars with enough force to send chunks of the planet's surface hurtling into space. Some of those debris fragments, now floating in the void, contain tiny microbes buried deep within the rock, shielded from radiation. Millions of years later, one of those fragments crashes into Earth, splashing down in a primordial ocean. The microbes, still dormant but alive, wake up in a new world, and the rest is evolutionary history. Here's the wild part. We know this kind of interplanetary travel isn't just possible, it's happened. Martian meteorites have been landing on Earth for billions of years. We've even identified some of them, like the famous LH-84001, which caused a media frenzy in the 90s when scientists claimed to have found fossilized bacteria inside. Though that claim remains controversial, the discovery proved one thing unequivocally: rocks can and do make the journey from Mars to Earth alive. laboratory tests show certain extremophile bacteria can survive the brutal acceleration of an asteroid impact, the vacuum of space, and even the fiery plunge through Earth's atmosphere if buried deep enough in the rock. But let's flip this script. If life could have come to Earth from Mars, could it have gone the other way? Billions of years ago, when both planets were wet and warm, Earth might have been the one seeding Mars. Early Earth was a volcanic, meteorite-battered chaos perfect for launching life-filled rocks into orbit. And if even a single microbe made it to Mars during its habitable window, it could have kick-started life there before the planet dried up. It's a cosmic game of ping-pong, with life as the ball. Now, here's where it gets really mind-bending. If life did hop between planets, we might all be Martians. The earliest evidence of life on Earth dates back nearly 4 billion years, right around the time when Mars was still habitable. Some scientists argue that Earth's environment was still too hostile at that point, with constant asteroid strikes boiling the oceans and scorching the land. Meanwhile, Mars, smaller and quicker to cool, could have offered a quieter, more stable nursery for life's first steps. If that's true, our search for life on Mars isn't just about finding aliens, it's about finding our own ancestors. Yet panspermia raises as many questions as it answers. Even if microbes could survive the journey, could they thrive on arrival? Mars and Earth, though similar in some ways, had different chemistries, temperatures, and levels of ultraviolet radiation. A microbe evolved for Martian brine pools might find Earth's early oceans as alien as we'd find the surface of Venus. And then there's the timing problem. For life to spread, both planets needed overlapping windows of habitability, something we're still working to pin down with geological evidence. The most tantalizing version of this theory goes beyond microbes. If simple life could hitch a ride between worlds, what about complex organisms or even intelligence? It's a staggering thought. Could an ancient Martian civilization, facing their dying planet, have deliberately sent genetic material or even AI-bearing probes to Earth to ensure their legacy? It's the ultimate twist on the panspermia idea, blending hard science with speculative wonder. Regardless of where life began, panspermia reshapes how we see our place in the cosmos. If life can jump between planets, then biology might not just be a local phenomenon, it could be a galactic inevitability, spreading like spores on the solar wind. Every time we find a new extremophile thriving in Earth's harshest corners, we're reminded that life is stubborn, adaptable, and maybe even interstellar. And if we one day dig up fossils on Mars that look eerily familiar, we might have to rewrite not just the history of two planets, but the story of life itself. The Fermi paradox has haunted astronomers for decades. If the universe is so vast and ancient, why haven't we found any trace of intelligent life beyond Earth? Mars twists that question into something even more intimate. Here's a planet right next door, one that might have once resembled Earth in its prime. If life flourished there, even briefly, why haven't we stumbled over undeniable relics of its existence? The methane mystery magnifies this puzzle. We're detecting gas that could signal biological activity, yet after decades of rovers, orbiters, and landers, there's no smoking gun, no fossilized cities, no discarded tools, not even a single unambiguous microbe. It's as if Mars is teasing us with clues while hiding the full story. Consider the numbers. Mars had liquid water for hundreds of millions of years, plenty of time for life to emerge and evolve. If Earth's history is any guide, simple microbes could have transformed the planet's chemistry, leaving behind layered sediments, mineral deposits, or atmospheric changes. Some argue we're seeing exactly that in the methane spikes and odd soil compositions. But the Fermi paradox demands more. Where are the ruins of Martian civilizations? The satellites in decaying orbits, the radioactive traces of ancient reactors, even microbial life should, in theory, spread and diversify enough to leave unmistakable chemical fingerprints. Yet every potential discovery, from the controversial microfossils in Martian meteorites to the fleeting whiffs of methane, remains stubbornly ambiguous. One explanation leans on time. Mars' window of surface habitability slammed shut over 3 billion years ago. Any civilizations rising there would have faced a slow-motion apocalypse as their atmosphere leaked into space and oceans froze solid. If they reached a technological level similar to ours, they'd have had centuries, maybe millennia, to find solutions. Underground refuges, climate engineering, or even interstellar exodus might have been their only options. In such a scenario, the lack of surface artifacts makes sense. Ruins exposed to Mars' sandblasting winds and cosmic radiation for billions of years would crumble to dust. Even deep structures could be buried under layers of sediment or ice. But there's a darker possibility. What if life on Mars never made it past the microbial stage? Earth took over 2 billion years to evolve complex cells. Mars might have run out of time before crossing that threshold. Without multicellular life, there'd be no builders, no engineers, no civilizations to leave behind traces beyond chemical oddities like methane. This would resolve the Fermi paradox for Mars in the bleakest way. The universe might be teeming with life, but almost none of it escapes simplicity before its planet turns hostile. Yet the methane keeps the debate alive. Its sporadic bursts don't fit neatly into purely geological explanations. If microbes are producing it today, they're masters of stealth, hiding in places we've barely explored, like deep aquifers or lava tubes. This raises another Fermi-inspired question. Could intelligence itself be rare, but life absurdly adaptable? Mars might be a planet where biology clings on in dark, isolated pockets, forever trapped in microbial form. No grand civilizations, just tenacious survivors eking out an existence beneath the radiation and dust. Perhaps the real lesson here is about patience. We've barely scratched Mars' surface, literally. The rovers have covered less ground than a tourist might stroll in an afternoon. Our orbiters map the planet at resolutions where a school bus would still be a blur. If Earth were being observed from space at this level of detail, would aliens even notice our pyramids, let alone our cities? The silence isn't proof of absence, just a reminder of how much searching remains. Every methane spike, every odd mineral formation, is a whisper from a world that might still hold answers. The Fermi paradox asks where everyone is. Mars replies, keep digging. Occam's razor, the principle that the simplest explanation is usually the right one, cuts through the methane mystery like a scalpel. On one side, we have the microbial theory, tiny, resilient organisms lurking beneath Mars' surface, farting methane as they eke out an existence in briny pockets. On the other, the far more sensational idea of an underground alien civilization venting gas as part of some unfathomable industry. Science favors the microbes, and not just because they're less flashy. The evidence, sparse as it is, points to a universe where life is tenacious but rarely glamorous. After all, we found microbes thriving in Earth's most hostile corners, inside nuclear reactors, at the bottom of acid lakes, even in rocks miles underground. If life exists on Mars, why wouldn't it follow the same humble blueprint? Yet simplicity doesn't always mean obvious. The microbial theory has its own complexities. For starters, We've yet to find a single shred of direct evidence, no cells, no fossils, no organic molecules in the soil that scream life. Methane alone is circumstantial at best. And then there's the gas's baffling behavior, those sudden spikes and disappearances that don't quite match how microbes produce methane on Earth. Some scientists argue that abiotic processes like serpentinization or meteorite impacts could mimic biological signatures just enough to keep us guessing. Occam's razor might prefer microbes, but Mars seems determined to muddy the waters. What's fascinating is how quickly the simplest explanation can unravel when you zoom in. Take the alien civilization theory. At first glance, it feels like pure fantasy, an unnecessary leap when microbes could suffice, but dig deeper and you hit unsettling questions. If microbes are producing methane, why haven't we found other organic byproducts? Why does the gas appear in such localized, inconsistent bursts? Could geology really account for all these quirks without stretching credibility? The alternative, that an intelligent species is behind it, is undeniably wild, but it's not impossible. After all, human industry pumps methane into Earth's atmosphere every day. If we vanished tomorrow, would aliens piecing together our existence dismiss our methane plumes as mere geology? Here's where Occam's razor meets its limits. The principle works beautifully in clean, controlled scenarios, but Mars is anything but. It's a planet with a fractured history, where water came and went, where volcanoes once roared and then fell silent, where the very ground might hide secrets we've barely begun to uncover. The simplest explanation isn't always the one that fits all the jagged pieces. That's the heart of the debate. Microbes are the safe bet, the answer that doesn't require rewriting textbooks. But safe doesn't always mean right. Science thrives on anomalies, on the data points that don't quite fit, and Mars methane is nothing if not an anomaly, a whisper of something we don't yet understand. Maybe it's microbes, maybe it's geology, or maybe, just maybe, it's something we haven't even thought of yet. The razor's edge is sharp, but Mars has always been a world that defies easy cuts. Humanity's obsession with Mars goes far beyond science. It's a mirror reflecting our deepest hopes, fears, and creative impulses. Long before rovers scratched the planet's surface, people were mapping not just landscapes, but entire civilizations onto that rusty disk in the sky. The story begins in earnest with Percival Lowell, a wealthy astronomer who turned his telescope toward Mars in the late 19th century and saw what he desperately wanted to see: canals. Not natural formations, but straight, artificial waterways crisscrossing the planet like an engineered irrigation network. Lowell published elaborate maps and books insisting these were the work of an advanced society struggling to survive on a drying world. Never mind that other astronomers saw nothing but blurry surface features. Lowell's vision captured the public imagination, spawning a century of Martian mania. What makes these theories so persistent isn't just faulty data, it's psychology. Mars sits in a sweet spot of cosmic familiarity, close enough to resemble Earth with seasons and polar ice, yet alien enough to spark speculation. When we stare at its surface, our pattern-seeking brains do what they've done for millennia: fill gaps with stories. The same instinct that saw faces in clouds or constellations in stars now projects crashed spaceships in rock formations and city ruins in eroded mesas. Modern conspiracy theorists echo Lowell's leaps, pointing to oddities like the D&M Pyramid or Face on Mars as proof of ancient builders. Never mind that high-resolution images reveal these to be ordinary landforms. The allure of hidden knowledge overrides evidence. Cultural narratives amplify this effect, from H.G. Wells' blood-drinking Martians in War of the Worlds to the heroic aliens of John Carter. Pop culture has conditioned us to see Mars not just as a planet, but as a character, sometimes menacing, sometimes noble, always mysterious. When NASA Viking landers failed to detect life in the 1970s, public disappointment was palpable. The scientific establishment declared Mars dead, but countercultures doubled down. Ufologists claimed the government was hiding evidence, pointing to anomalies like the Mars cube or alien thigh bone photographed by rovers. These theories thrive because they offer something science often struggles to provide: a sense of wonder and immediacy. Microbial fossils can't compete with the drama of pyramids and portals. Underlying it all is a fundamental human anxiety, the terror of cosmic loneliness. If Mars, our closest sibling, turned out to be as barren as the Moon, what does that say about life's rarity in the universe? Conspiracy theories become psychological armor against that existential dread. They transform cold data into a treasure hunt, where every grainy image might hold the key to humanity's greatest question: are we alone? The methane mystery plays perfectly into this dynamic. It's a scientific enigma vague enough to fuel endless speculation, yet tangible enough to feel revelatory. The irony is that the truth, whatever it may be, is likely stranger than fiction. If microbial life exists beneath Mars' surface, that discovery would revolutionize biology. If serpentinization or some unknown geochemical process explains the methane, it rewrites planetary science. Yet for some, these authentic mysteries lack the visceral thrill of ancient astronaut theories. The challenge for scientists isn't just exploring Mars, it's communicating wonders that don't need embellishment to captivate. After all, a single living cell in Martian soil would be the most profound discovery in human history. No pyramids required. NASA isn't content to let Mars keep its secrets, not when the methane mystery dangles like a cosmic carrot. The next decade of missions reads like a sci-fi wish list, each one designed to peel back another layer of the red planet's enigma. At the top of the roster, the Mars Sample Return Campaign, an ambitious handoff between robots that could finally bring pieces of Mars back to Earth's labs. Imagine Perseverance, already collecting tubes of Martian soil and rock, leaving its treasure trove for a future fetch rover to scoop up. That rover would then deliver the samples to a small rocket, which would blast them into orbit, where yet another spacecraft would catch them like a cosmic relay baton before racing home. It's a Rube Goldberg machine of planetary science, but if it works, those pristine samples could hold the smoking gun, organic molecules trapped in ancient sediment, or even fossilized microbes clinging to mineral veins. But why wait for samples when you can send the lab to Mars? Enter the Mars Life Explorer, a concept mission now under serious study. This nuclear-powered lander would carry a drill capable of reaching 2 meters below the surface, deep enough to punch through the radiation-sterilized top layer and into soils where any surviving microbes might lurk. Its onboard instruments could analyze the chemistry of those hidden layers in real time, sniffing for amino acids, lipids, or other telltale signs of biology. Even more tantalizing, it might catch methane production in the act, measuring how concentrations fluctuate with temperature and depth. Then there's the wild card, Dragonfly. While this rotorcraft is destined for Saturn's moon Titan, its success could revolutionize how we explore Mars. Picture a drone, not unlike the Ingenuity helicopter that's already buzzing across Jezero crater, but larger and loaded with sensors. Future Mars drones might flit between methane hotspots, sampling plumes at different altitudes and times of day to map how the gas moves and dissipates. Unlike rovers, which crawl at a snail's pace, aerial platforms could cover vast distances in hours, checking out that strange fissure or pit that just vented methane before the trail goes cold. The European Space Agency isn't sitting this out either. Their Rosalind Franklin rover, set to launch in 2028, carries a drill that can reach even deeper 2 full meters, and an onboard lab designed specifically to detect organic material. But here's the kicker: it's targeting Oxyoplanum, a clay-rich region that may have once been a river delta. If Martian microbes ever thrived here, their molecular ghosts might still linger in those water-altered minerals. The rover's suite of spectrometers could spot the chemical fingerprints of past or even present life, all while monitoring the air for methane whiffs that match Curiosity's sporadic detections. And let's not forget the orbiters. NAS, a planned Mars Atmosphere and Volatile Evolution Mission 2, or MEVEN2, aims to solve the methane disappearing act by studying how the planet's upper atmosphere interacts with solar wind. If methane is being torn apart by charged particles or chemical reactions, MEVEN2 might catch the process in action, revealing whether the gas is being destroyed faster than expected, or if it's somehow replenished from below. What ties all these missions together is a single, burning question: context. Right now, each methane detection feels like hearing one note of a symphony played through a wall. Is it biology, geology, something we haven't even imagined? By combining deep drilling, atmospheric monitoring, aerial scouting, and sample returns, these missions won't just gather data, they'll weave a story. A story that might end with humanity's greatest discovery or its most humbling near miss. Either way, the hunt is on, and Mars' days as a silent enigma are numbered. Drilling into Mars isn't like digging into Earth's soft soil. It's more like trying to crack open a cosmic vault sealed for billions of years. The planet's surface is a gauntlet of razor-sharp rocks, abrasive dust, and temperatures that swing from bone-chilling cold to oven-like heat in a single day. But the real challenge lies deeper, where the answers to the methane mystery might be hiding. To find conclusive proof of life, or even the controversial possibility of alien technology, we'd need to penetrate meters below the surface, into layers untouched by the radiation that sterilizes the topsoil. And that's where the problems start. Take NASA InSight lander, which tried to hammer a heat probe into Mars' crust in 2018. The probe, nicknamed the Mole, was designed to burrow up to 5 meters deep, measuring the planet's internal temperature. But Mars had other plans. Instead of loose, sandy soil, the Mole hit a slab of cemented dirt as hard as concrete, bouncing back like a nail struck against a brick. After 2 years of futile hammering, the mission was declared a failure. If something as simple as a heat probe couldn't make progress, how will future drills reach the depths where microbes, or more, might lurk? The stakes are even higher when you consider contamination. Earth is filthy with microbes, and every drill bit, every rover wheel, carries the risk of seeding Mars with our bacteria. That's not just bad science, it's a potential planetary crime. Imagine drilling into a pristine Martian aquifer, only to find Escherichia coli from Florida clinging to your equipment. To prevent this, spacecraft undergo brutal sterilization, baked at extreme temperatures or doused in radiation. But drills pose a unique problem. Their moving parts can't be fully sterilized without destroying them. It's a paradox. The tool we need to find life might accidentally bring it along for the ride. Then there's the energy problem. Drilling on Earth is power-hungry, relying on massive rigs and constant human maintenance. On Mars, drills must be lightweight, energy efficient, and able to operate autonomously for months. Some proposals lean on nuclear power, like the Mars Life Explorer concept, which would use a compact radioisotope heater to keep its drill warm in the freezing cold. Others suggest lasers or sonic drills that vibrate through rock without physical bits that could snap. But even these futuristic tools face a brutal truth: Mars geology is a mystery. Without knowing exactly how deep to dig or where to aim, we're essentially drilling blind. And what if we do hit pay dirt? Suppose a drill strikes an underground reservoir or a lava tube layered with strange minerals. How would we recognize alien artifacts if they don't match anything in our earthly experience? On Earth, archaeologists identify ancient tools by their symmetry, wear patterns, or material. But an alien civilization might have used technologies so advanced, or so alien, that their remnants look like natural formations to us. Imagine future rovers rolling past what they think is just another odd rock, when in reality, it's the rusted husk of a machine built 1 billion years ago. This isn't just science fiction. In 2022, researchers tested AI algorithms to spot Technosignatures, unnatural patterns in geology that might indicate intelligence. The results were sobering. Without clear rules for what counts as an artifact, even the smartest software struggles. Add Mars erosion and radiation, which could degrade any structures into ambiguous lumps, and the search becomes a needle in a haystack problem where the needle might not even look like metal anymore. Yet for all these hurdles, the payoff would rewrite history. A single drill core packed with microbial fossils, or better yet, living cells, would prove that life isn't confined to Earth. And if by some wild chance we uncovered something more, a crystal with unnatural facets, a metal alloy with no volcanic origin, the implications would shake humanity to its core. That's why we keep trying, why rovers like Rosalind Franklin will keep grinding away, why engineers dream of mile-deep drills, and why every speck of Martian dust holds a story we're dying to read. The subsurface might be Mars' last great fortress, but behind its walls could lie truths worth every broken drill bit. Finding life on Mars wouldn't just be a scientific breakthrough, it would force humanity to confront questions we've never had to answer before. What rights would Martian microbes possess? If we discovered intelligent beings beneath the surface, would we have the moral authority to study them? Or would they deserve the same ethical considerations as human societies? These aren't thought experiments anymore. With drills poised to penetrate deeper into Mars' crust, we're potentially years away from facing these dilemmas in reality. Consider the simplest scenario: a fossilized microbe. Even this tiny relic would trigger heated debates. Should Mars become a planetary preserve, off-limits to mining or colonization to protect potential ecosystems? On Earth, we've learned the hard way how easily delicate biological networks collapse under human interference. The Antarctic Treaty System already sets precedent, protecting fragile environments from exploitation. Would Mars require similar safeguards, enforced across national space agencies and private corporations? The challenge escalates when you realize we might not recognize living Martian organisms at first glance. Their biochemistry could be so alien that early tests miss them entirely, leading to accidental contamination or destruction before we understand what we've found. Now imagine the seismic shift if we found more than fossils, active microbial communities thriving in underground brines. Suddenly, planetary protection takes on new urgency. Drilling operations could introduce Earth bacteria that outcompete native life, causing an interplanetary extinction event. Some scientists argue we'd need to treat Mars with the same caution as an uncontacted indigenous tribe, observing from a distance to avoid cultural, or in this case, biological contamination. But how do you balance restraint with the burning human impulse to explore? There's no playbook for this. The Outer Space Treaty of 1967 vaguely prohibits harmful contamination, but never anticipated we'd find actual ecosystems to protect. The ethical maze grows infinitely more complex if the methane traces lead us to intelligent life. Picture uncovering an underground civilization, perhaps one that never developed spaceflight but built intricate societies in lava tube networks. Do we announce ourselves, risking the destabilization of their culture through what anthropologists call first contact shock? History offers grim parallels when advanced civilizations encountered isolated human tribes. The results often included disease, exploitation, and erasure. The prime directive from Star Trek was fiction's answer to this dilemma, but real-world science has no such guidelines. Some ethicists propose sending passive observation probes for decades before any interaction, while others warn that merely detecting our orbiters could trigger societal collapse if their belief systems can't reconcile alien existence. Even the act of studying Martian life raises moral questions. Would extracting samples for Earth labs be equivalent to taking indigenous people as museum specimens during colonial times? Astrobiologist Dr. Alfonso de Villa likens it to the early days of microbiology, when scientists discovered bacteria by the millions but initially dismissed them as unimportant. We might be standing on the brink of making that same arrogant mistake with Martian life, he warns, judging its value by how closely it resembles ours. This perspective shift could redefine our place in the cosmos not as pinnacle of evolution, but as one thread in a vast universal tapestry of life. The philosophical implications ripple outward. Confirmation that life arose independently on Mars would strongly suggest the universe teems with biology, transforming our search for meaning. Religions would grapple with doctrines shaped around Earth's uniqueness. Governments might race to establish property rights over extraterrestrial organisms, while bioethicists push for interspecies rights frameworks. The very definition of life could expand beyond carbon-based, water-dependent models, forcing updates to medical protocols and environmental laws written with only earthly biology in mind. Perhaps the most profound question is whether we'll recognize our moral obligations in time. Humanity's track record with newly discovered life forms, from driving the dodo to extinction to patenting genetically modified organisms, doesn't inspire confidence. The methane signatures swirling through Mars' atmosphere might be more than a scientific puzzle. They could be the first faint signals in a cosmic test of our species' maturity. Whether we pass may depend not just on our technological prowess, but on our ability to approach the unknown with humility rather than conquest. After millennia of wondering if we're alone, we may soon need to answer a harder question: are we ready to not be? Long before scientists debated methane spikes, storytellers were populating Mars with civilizations, some benevolent, others terrifying, all reflecting humanity's deepest hopes and fears about what might lurk next door. The granddaddy of Martian invasion tales, H.G. Wells' 1898 novel The War of the Worlds, didn't just entertain, it seared an image into our collective psyche. Those towering tripods vaporizing Victorian England weren't mere monsters. They embodied colonial anxieties turned upside down. For a British Empire used to conquering, Wells asked what it might feel like to be the conquered. His Martians weren't just aliens, they were dark mirrors, showing humanity its own capacity for destruction, and that eerie red weed spreading across the countryside. A haunting preview of how alien biology might overwhelm our own. Flash forward to 1953, when Orson Welles' infamous radio adaptation proved these ideas could still panic modern audiences. Thousands of listeners genuinely believed Martians were attacking New Jersey, revealing how easily the line between science, fiction, and perceived reality blurs when that crimson planet's involved. This cultural conditioning runs deep, so deep that when a Viking landers found Mars barren in the 1970s, public disappointment bordered on betrayal. We've been promised canals and cities, not rocks and dust. But not all Martian fiction leans apocalyptic. Ray Bradbury's 1950 The Martian Chronicles painted a far more poetic vision, a dying civilization of ethereal, telepathic beings who blended into their environment like living sand sculptures. Their tragedy wasn't warfare, but inevitability. Their culture faded like whispers in thin air as humans encroached. Bradbury's Martians didn't need methane spikes to feel real. Their melancholy humanity made them breathe on the page. This tradition continues in modern works like Andy Weir's The Martian, where the planet itself becomes the antagonist, a sterile yet stunning landscape where every breath and calorie must be fought for. Film amplifies these ideas with visceral impact. The 1990 Total Recall, both versions, posits Mars as a corporate colony sitting atop alien technology, a buried reactor hinting at lost greatness. That iconic scene of the atmosphere shield activating, turning Mars' sky blue, taps into our longing to terraform dead worlds. Meanwhile, Red Planet 2000 and Mission to Mars 2000 played with the idea of microbial life as both discovery and threat, foreshadowing real scientific debates about planetary protection. Perhaps most provocative is the 2015 novel The Three-Body Problem by Liu Cixin, where a virtual reality game set on a chaotic alien world implied to be Mars becomes a recruitment tool for first contact. The book's depiction of a civilization surviving environmental collapse through ruthless adaptability feels uncomfortably relevant today. These stories do more than entertain, they shape how we interpret the data. When scientists debate whether Mars methane could be industrial, they're unknowingly channeling a century of speculative fiction. The irony: these fictional portrayals might be preparing us for realities stranger than we've dared imagine. When the Phoenix lander discovered perchlorates in Mars soil in 2008, chemists recognized them as potential energy sources for microbes. Sci-fi had already explored this concept in the X-Files episode Space, where Martian bacteria hitched rides on spacecraft. Life finds a way, whether in Arthur C. Clarke's imagination or a JPL laboratory. What makes these narratives endure isn't their accuracy, but their ability to frame Mars as a character rather than a rock. From Wells' imperialist invaders to Matt Damon's stranded botanist, our fictional Martians reflect who we are at any given moment: colonialists, explorers, survivors. And as the methane mystery deepens, one thing's certain: whatever we eventually find, we'll understand it through stories told long before the first rover ever rolled. The moment scientists announce definitive proof that Mars methane comes from an alien civilization, the world would erupt in a frenzy unlike anything we've seen before. Social media platforms would instantly overload with hashtags like #MartianLife and #FirstContact, while news channels scramble to assemble panels of experts, some sober scientists urging caution, others wild-eyed theorists claiming they knew it all along. The initial wave would be euphoria, a collective gasp of awe at the universe becoming infinitely stranger and more wondrous. People would gather in public squares, staring up at the night sky with newfound reverence, whispering, "They're right there." But history warns us this excitement could curdle into something darker. Remember the panic that swept America in 1938 when Orson Welles' War of the Worlds broadcast tricked thousands into believing Martians had landed in New Jersey. Streets flooded with terrified families clutching radios, convinced death rays were vaporizing cities just beyond the horizon. The hysteria wasn't just about aliens, it was about helplessness. Listeners had no context, no authorities to trust, just a voice on the radio describing the unimaginable. Fast forward to today, and the ingredients for chaos are even more potent. Hyper-connected misinformation networks, deepfake technology, and governments with spotty records of transparency. Imagine conspiracy videos alleging the discovery was leaked to hide an imminent invasion, or religious groups proclaiming the end times. Financial markets would reel with volatility. Space industry stocks might skyrocket overnight, while sectors tied to terrestrial security could crash as investors brace for geopolitical upheaval. Countries might hoard resources, fearing Mars could become the next colonial frontier, sparking a silent space race under the guise of scientific collaboration. Conspiracy theories would metastasize claims that NASA are known for decades, or that the aliens are already among us, wearing human skin. The very uncertainty would be weaponized. Politicians might stoke fear to push through surveillance laws for planetary defense, while media outlets churn out doomsday clickbait. Yet amid the noise, quieter revolutions would unfold. Philosophers and theologians would wrestle with existential questions. Does humanity's centrality in creation vanish if our neighbors are microbial, or worse, smarter than us? Protesters might demand Mars be declared a sovereign alien nation, while corporations lobby to mine its resources before regulations freeze them out. Schools would rewrite biology textbooks overnight, and astroethics would become a mandatory course. The most profound shift, though, might be in how we see ourselves. For centuries, we've wondered if we're alone. To have that question answered with a "no" would unravel something fundamental in the human psyche, replacing loneliness with a terror, or perhaps a thrill, that we were never special to begin with. The irony, Martian microbes wouldn't care. They'd keep metabolizing in their briny pockets, oblivious to the chaos, their existence unleashed on a pale blue dot they'd never see. And that contrast between cosmic indifference and human frenzy might be the most humbling lesson of all. So where does that leave us, staring at a cosmic crime scene, dusting for fingerprints, with two prime suspects, each capable of rewriting history? On one side, the microbial theory, tiny, unassuming life forms clinging to existence beneath Mars' frozen surface, turning rocks into methane through chemistry as old as life itself. If proven true, it would mean life isn't a fluke confined to Earth, but a cosmic inevitability, sprouting wherever there's even a whisper of water and energy. Picture the implications: every icy moon, every exoplanet in the Goldilocks zone suddenly buzzing with potential. We'd go from a lonely outpost in the void to neighbors in a galaxy teeming with quiet, subterranean ecosystems. And then there's the other suspect, the one that sends shivers down the spine, the possibility that Mars methane isn't biological at all, but industrial. A sign not of nature's persistence, but of intelligence's triumph over a dying world. if by some wild chance an underground civilization is venting gases as they go about their unfathomable business, the revelation would dwarf every discovery in human history. Not just because we're not alone, but because it would prove that civilizations can outlast their planet's death, retreating into the dark, adapting, surviving. The Fermi paradox would crack open overnight, forcing us to ask, who else is out there, hiding in plain sight? Here's the twist: both theories, no matter how opposed, lead to the same humbling truth. Whether it's microbes or Martians, the universe is far stranger and more resilient than we ever imagined. Life, simple or sophisticated, doesn't just exist in paradise. It thrives in acid, survives in vacuum, lingers in radiation. It tunnels under deserts, builds cities in lava tubes, redefines what habitable even means. And Mars, that rusty enigma next door, is holding the key. The beauty of this mystery is that it won't stay unsolved forever. Rovers are drilling, orbiters are mapping. Sample tubes are waiting for their ride home. Every new mission is another turn of the lock, another step toward knowing whether that flicker of methane is a microbe's breath or a machine's sigh. Until then, the question hangs in the thin Martian air: who's there? The answer might not just change how we see Mars, it might change how we see ourselves. So keep watching the sky, keep following those distant robots as they sniff and scrape and dig, because somewhere amid the dust and shadows of that red world, something is speaking in gas. And one day, very soon, we'll finally understand what it's trying to say. So, what's your verdict? Microbial farts or an underground alien metropolis? Hit that poll up top and cast your vote. This mystery isn't just for scientists in lab coats. It's for all of us to chew on. Maybe you're Team Microbe, betting on those tough little extremophiles huddled in salty Martian puddles. Or maybe you're swinging for the fences with Team Alien, convinced there's something or someone down there venting methane like a cosmic exhaust pipe. Either way, drop your wildest theories in the comments. Did we miss a crucial clue? Is there a rogue scientist's paper from 1982 that explains everything? Spill it. This debate's just getting started. And stay tuned, because Mars isn't done messing with us. Up next, we're diving into another head-scratcher: the haunting case of the Martian ghost craters. Imagine giant, perfectly circular scars on the planet's surface, except there's no crater left. Just a phantom imprint whispering of ancient impacts erased by time. What wiped them clean? Water, wind, or something even weirder? Hit subscribe so you don't miss it. The red planet's got secrets piled on secrets, and we're just getting to the good stuff. Oh, and if you've got a friend who still thinks Mars is just a boring desert, do them a favor, share this video. Watch their jaw drop when they realize we're this close to answering one of humanity's oldest questions: are we alone? Now, go forth and argue passionately in those comments. The truth is out there, and maybe, just maybe, it's closer than